Hello, everyone, and welcome to the webinar on virtualizing high-performance applications and GPUs. My name is Keith Parker. I'm the Director of Product Marketing here at Pavilion. And joining us today will be Jason Massey and Justin Murray, both Technical Marketing Architects with VMware, as well as Walter Hitton, Director of Product and Solution Marketing here at Pavilion. Just a little bit of housekeeping. This presentation will be recorded, and a recording will be made available to all registrants. During this presentation, all attendees will be on mute. If you do have any questions, please feel free to put them into the chat function, and we will be sure to answer those during the Q&A session at the end. With that, I'd like to introduce Walt Hitton. Thank you.
Hey, Keith, thanks very much. And Jason and Justin, thanks for joining, and all people who are participants today. I think we've got a really interesting webinar to talk about virtualization for high-performance applications, and also what it means for GPU technologies. So I'm going to talk just a little bit about what's happening with machine learning and AI and GPUs in the enterprise. Frankly, it's affecting everything from recommendation engines to how we go about doing research to how we do fraud detection. All of this is very real and having a very big impact. And at the same time, there's a lot of work involved with deploying AI in enterprise at scale and doing it in a way that has a strong return on investment. So one of the things that we'll get into today is, not only a little bit more about how vSphere 7 enables high performance, but also how we can share, aggregate, and orchestrate GPUs across the enterprise for the most effective AI ML outcomes. So it really started with about this time last year when VMware introduced vSphere 7, and vSphere 7 is, as Scott Sinclair so nicely says, really brought NVMe over fabrics into the mainstream. But what that really means is we're now taking advantage of remote direct memory access between storage devices and between server systems, where we have networks that look lossless. We have performance that is extraordinary with very low latencies. So really a game changer, and there have been many enhancements since that time. But I think what I'd like to do right now is turn it over to Jason and have him talk some about VMware, NVMe over fabrics, and vSphere 7. So go ahead, Jason.
All right, thanks, Walter. So like Walter said, with vSphere 7, we released NVMe over fabrics. And really the big driver for that is a lot of the flash manufacturers are moving towards NVMe devices. Well, when you're using an NVMe device, right, it's a different connectivity. It's a different type of a bus. And the big benefit of this is the way you access that flash itself. Unlike with traditional SCSI, where you've got more of a serialized access and you're kind of queuing into getting into that device, with NVMe, we have a substantial amount of parallelism, right? Depending on the types of devices and how the connectivity works, you can have up to 64,000 queues and 64,000 commands per queue. So you can understand why we want to move towards this type of connectivity to be able to take advantage of these type of devices. Now, with the initial release of vSphere 7 for the NVMe over fabrics connectivity, we added FC and RoCE, so the RDMA over converged Ethernet. And so with that, when customers are starting to look into kind of what are the differences, right, between the way that these devices are accessed, right? There's a lot of commonality that a lot of administrators are comfortable with or know the commands, right? Active, optimize, not optimize, standby, unavailable. And we have a couple of different modes that we can access. We have active, and then we have asymmetrical namespace access. And so when we kind of look at those, you can see here the comparison between a standard SCSI Alua state versus the NVMe ANA state. And so it just kind of gives you some of the differences and or similarities when we talk about, certain states within these physical devices. So as we start thinking about this, it's how we can get this higher performance by using, again, that NVMe protocol rather than the SCSI protocol. So let's go to next. Now, like I said, the initial support is FC and RDMA. Now, as far as the FC goes, that's pretty straightforward. As long as your HBA and your fiber environment support NVMe over Fabrics functionality, there's not a lot of setup that needs to be done. There's a little more setup on the RDMA, but what the RDMA gives us is, again, that memory direct access between the virtual environment and the storage environment. And so there's a lot of latency that is inherently removed because we're not having to go through so many different translation layers. So instead of, going through storage stack to the virtualization down to, some type of transport layer, we're bypassing a lot of that. And just by doing that, we're reducing significant amounts of cycles. And so that inherently right there gives us a bunch of performance, which then lets us take advantage of the performance of NVMe devices. Let's go next. Now, there are a couple of caveats when you're setting up NVMe over Fabrics using RoCE or RDMA. It's really important that your network is set up with the lossless functionality. And there's a lot of documents, and I've got some resources available here in a bit that show you and give you all of the details on setting this up. But just really quickly, there are some of the specific requirements is that you must use an RDNIC, so an RDMA network device. That's very critical, and it must only be used for the NVMe over Fabrics functionality. It can't be shared with another functionality at this time. Another piece is that the way that you set this up is you have a separate switch for each NIC and each kernel binding. It isn't similar to SCSI or iSCSI, where you can do, port binding. This is a very direct binding setup for the NVMe over Fabrics RoCE configuration. And so it's very important that when you're thinking about this, that you understand some of these requirements, both on the network side and some of the hardware functionality that you have to have within your host. So let's go to the next. So there's like I said, FC, RDMA, but really what we want to kind of think about is what are currently not supported. RDMs are not supported using NVMe over Fabrics, shared VMDKs, vVols, although that is something we are looking at. A lot of the VAI plugins aren't supported. And then using the NVMe namespace or a provisioning can't be used for core dumps. Now, I've created a page here that has a whole bunch of resources for VMware and NVMe over Fabrics, and there's also some links to our partner pages. So you can also see links to Pavilion's page on NVMe over Fabrics. And so hopefully if you need any information, I've got information in there. If I don't, please let me know. I'll add it. This is an active page that I try and keep current. With that, I'll hand it over to, we have one more. So I do want to show this, and this is a great example of showing just the performance difference just from changing from iSCSI to RoCE. You can see the substantial drop in latency and the performance that you gain in IOPS just by changing the protocol. And this is really where I was talking about earlier about that. Just by changing this protocol, not having to go through these stacks, and also being able to use the NVMe functionality, we inherently get quite a bit of performance increase and reduced latency. And so you can see why there's a lot of customers that when they have really latency sensitive applications or environments, this is where we're seeing customers go, where they need maximum performance and absolute lowest possible latency. And so this is why a lot of the customers are really interested in the NVMe over fabrics and the RoCE protocol and connectivity. So, all right, now we can hand it over to Justin to jump into some of the NVIDIA information.
Thank you, Jason. Very interesting presentation. Thank you. I'm Justin Murray from the technical marketing team at VMware, and I'll talk a little bit about the work we're doing at VMware with NVIDIA specifically, mainly about GPUs, but also I'll connect into the RDMA and RoCE themes that Jason talked about in a slightly different way. Use of those for access between GPUs and network cards, for example, and between two GPUs that are on different host servers in this case. So as Walt mentioned earlier, we launched vSphere 7 last year. In March of this year, 2021, we launched vSphere 7 Update 2. And that was a big launch for us, but it was also themed very much around a cooperation that started last year with NVIDIA, a very much tighter cooperation than has been the case over the last 7-8 years that we've been working with NVIDIA. So the two CEOs got together and agreed to work together to really democratize machine learning in the enterprise. And that's a big task. And these are some of the items that came out of that. Firstly, NVIDIA has launched a whole new family of GPUs in the past year called the Ampere family, the A100, the A30, etc. And those are all now fully supported on vSphere 7 Update 2. And they provide really excellent performance. The A100 is twice the performance of the previous top of the range, the V100 that previously existed in the NVIDIA suite. We can also do virtual GPUs on there and therefore do vMotion, and DRS is intelligent about placing a VM with a virtual GPU in it onto a particular host. That gives you the capability to suspend the workload and resume it later on, which is very useful if you're going to be interchanging different data science jobs across your infrastructure. And this is evidence that SRIOV, which we'll come back to later, is becoming a core underlying infrastructure at the BIOS level now for virtual GPUs. And what it gives us is better separation between two consumers of the same physical GPU. In case you're wondering, graphical processing units are de facto standard in machine learning today for applications like image processing that Walt showed you, natural language recognition like responding to phone calls in data centers, and many, many other applications. And GPUs are almost essential components now of machine learning. And virtual GPUs are simply those same physical GPUs presented in part or in whole to a virtual machine on VMware. And we've been doing that for quite some time. Some deeper down enhancements that we made in vSphere 7 Update 2 was to do with GPU Direct RDMA, in fact, which is a mechanism supported by NVIDIA for allowing peer-to-peer communication to be speeded up within a server and therefore across servers as well. And that makes use of a PCI technology called Address Translation Service that I'll get into later. Effectively, I mentioned that you can use fractions of a GPU. So the A100 is particularly, the newest device, is particularly friendly to that because it has fractions at the hardware level called GPU instances, which we make use of under the covers of the vGPU. You can do multiple full GPUs up to 4 on one VM if you wanted to. That's for really high-end training where your machine learning model its parameters take up the full memory and more than the full memory of a GPU. You might use multiple GPUs for that. And you can affect the scheduling algorithms if you want to. And multi-instance GPU is the newest technology here, which, as I said, splits up the hardware inside one GPU into up to 7 different pieces. And we'll see that later and see why it's useful. Next slide, please. So along with all that, NVIDIA and VMware got together and recognizing the 3 factors that Walt mentioned, the risks, the performance concerns, and the scaling concerns that people have about machine learning in general, not just when you virtualize it. We, with NVIDIA, looked at our 2 communities, the data scientist community on the top left-hand side, the IT and VMware admin person on the bottom right-hand side, and said, how can we satisfy both of these communities together? How can we produce something that will make the IT admin capable of delivering the right infrastructure to data scientists to satisfy them? And so this is the end result of that work that we've been doing with NVIDIA over the past year or so. It's called the NVIDIA AI Enterprise Suite, and it's a combination of technology from NVIDIA, including virtual GPUs that you heard me talk about, but also a whole bunch of AI and data analytics frameworks that I'll show you in the next slide, and some performance testing that we're doing together. Let's go back to the previous slide for 1 second here. So all of that is leveraged on top of VMware vSphere with Tanzu, which is the Kubernetes embedded Kubernetes in vSphere. Now, you can choose to do this with just regular containers if you want to, but what we will offer you is the ability to orchestrate those containers and manage them using Tanzu, and that's in early access right now and coming soon. All of this, of course, depends on GPUs, and NVIDIA GPUs are virtualizable. You can produce a virtual GPU to represent part or whole of a physical GPU, and also it's based on the smart NIC technology that NVIDIA is now producing as a result of their acquisition with Mellanox. So that's where the RDMA ties in, and I'll show you that in a slide or 2 from now. So we want to dig deeper into that top layer there, the AI and data analytics, the GPU virtualization and performance scaling. And for that, I wanted to show you a new suite from NVIDIA, which is in the next slide, please, Walt. This is the NVIDIA AI Enterprise Suite of software. The tools for the data scientists are there at the top. Most data scientists are using TensorFlow or PyTorch or Caffe, these frameworks that allow you to develop machine learning applications very quickly. And they effectively hide away the details of GPUs and CUDA, the APIs used to access GPUs, and distribution even, they hide away the details of that so that you can build your application to port it onto many different infrastructures. Alongside those, there are specialized tools from NVIDIA like Triton Inference Server for deploying your ML application into production at scale, TensorRT, which you can think of as an optimizing compiler for speeding up your model. Transfer Learning Toolkit allows you to take pre-trained models, pre-trained machine learning models, and retrain them with your own specific data. So you're not starting from scratch anymore. And Rapids is a library and runtime for access to tabular data for data preparation, the first phase of machine learning. Machine learning is usually data preparation, data cleansing, ETL. Rapids is very good at that. And that's a recognition by NVIDIA that not just images and voice, but regular tabular data is important as well. So that's the upper layer. That's the offering to the data scientist. In the middle, you have the middleware tier, which are operators. Operators are a term in Kubernetes to refer to both the installation and management of some subsystems in a Kubernetes cluster. Here, what we're doing is installing all the GPU drivers and resulting libraries and all the network drivers and resulting libraries in these 2 operators, which will be relevant to you when you adopt Kubernetes, and taking the concerns about drivers out of your sphere, basically. And at the bottom, the important point to begin with is NVIDIA Virtual GPU, which I'll explain in detail. That's the ability to share a physical GPU across more than 1 VM on the same host. The other APIs there, like CUDA, CUDA has been around for many years. It's the API for accessing GPUs for machine learning. Magnum is the networking API, and Doka is the API for accessing these converged cards, these new cards that have both an ARM processor and a GPU on them, and a network card on them as well. So that's the stack of software and hardware innovations from the two companies. Quite an impressive thing. It's in early access as we speak here in May of 2021. It'll be shipping in a few months' time. So that's a new product that you're going to see coming out of NVIDIA, supported by VMware, exclusively certified on vSphere 7, update 2 and later, by the way. Okay, next slide. So the second, well, that whole thing was to reduce the risk for data scientists and VI admins. The risk was the main first point that Walt made earlier. What about performance? Well, NVIDIA has invested a ton of engineering time into performance testing, and VMware likewise is got a team of people working on performance testing of machine learning with GPUs on VMware. And this is a result from some NVIDIA testing done at launch time, actually in March, and it's continuing to be worked on. And what these nodes are nodes, each of which is a machine with a virtual machine running on it within a cluster. So this is the high end of training. This is distributed training here. And these machines are talking to each other over RoCE. They're using NVIDIA virtual GPUs with a 40C profile, as you see on the bottom right-hand side there. What that means is they're using the full GPU in each case. And they're executing a machine learning task called ResNet 50, which is a very famous benchmark based on TensorFlow and using floating point 16. And the important point is the green bars are pretty much parallel and equal to the gray bars, where higher is better, which means a virtualized system scales in pretty much the same way, very, very little difference in the low single-digit percentages. We scale on virtual just like bare metal scales. And on each of the cluster sizes from 1 node to 4 nodes, we're pretty much equal to bare metal. So that's the removal of the performance concern. And what you get from virtualizing, you get all of the management that you've been applying to your traditional applications in the data center, but you get vMotion and DRS initial placement as well. So the point here is that you don't lose any performance, but you gain the ability to bring this machine learning workload into the mainstream of your data center now and treat it as you do other workloads that you manage using vSphere. Next slide. So how do these pieces all come together into one flow? On the left-hand side, you have a developer working on computer vision or speech recognition or recommender engines. You know, when I came into this field a couple of years ago, I realized recommending engines like you would get from an online store, this is a whole field in itself with a vast number of people working on it. And GAN stands for Generative Adversarial Networks, which is a kind of a niche area in machine learning where, for example, images are created of people that are completely synthesized. They have never existed as people. That's a synthesized image there of someone who doesn't really exist. That's where these neural networks are capable of now, and constructing sentences on their own, for example, is a new field that the transformer type of neural network can do. Now, these are applications that I took as samples. There are many, many dozens of applications outside of these, but you're going to be building these in PyTorch or TensorFlow, which you'll typically do in Python or one of the other languages like it. And then you may choose to take a previously existing trained model from NVIDIA's library, which is on their NVIDIA GPU Cloud, NGC, and transfer that into your own mechanism and retrain it. For example, NVIDIA has done lots of work in computer vision for analyzing patterns of traffic on the roads or analyzing images of medical images, for example. You don't need to start from scratch here. You can take a pre-trained network, neural network, and then apply your own data to it and have it specialized for your particular field. Once you've done that, you'll want to optimize your neural network, which is quite a complex piece of delivery, optimize that for performance, and TensorRT does that. And finally, you're going to need a scalable platform to deploy it on. That's what the Triton Inference Server is. It has a multi-threaded approach, a multi-model approach, and a multi-version approach, so that many hundreds of models can be deployed at once using this inference server and served up to end users over protocols like gRPC, the remote procedure call from Google, for example. So this is the sort of end-to-end data science workflow is how I look at it. This is starting at development and going to production or inference deployment on the right-hand side using all of the toolkit that you're getting from the NVIDIA AI Enterprise Suite that I mentioned earlier. Next slide, please. If we were to delve into the VMware NVIDIA interface here into the virtual GPUs that are core to all this. Sharing GPUs is a strength of VMware. It's also a strength of NVIDIA now with the A100. Effectively, what's happening is that TensorFlow application at the top is making CUDA calls under the cover. CUDA is an API that is a standard for accessing NVIDIA GPUs. And those CUDA calls are being trapped by a guest driver handled by it. That's a guest inside the operating system. And those calls are being passed on to a second driver that exists inside ESXi itself. It's installed using a VIB or VMware Install Bundle. And that second driver is providing access control and saying, how much of this physical GPU exactly is this VM capable of or allowed to access? Is it 1/2 or 1/4 or 1/16 of the GPU? Or is it allowed to access all of the GPU? It's an access control mechanism. Once it's allowed the VM to access the GPU, it steps out of the way, and then the guest driver is driving that GPU as hard as if it were bare metal. That's why we're getting such good performance, is that the virtualization layer is not really slowing things down here. Yeah, the host driver steps out of the way and allows the guest driver to access the GPU. And from there onwards, you're operating at full speed. So the GPU receives the request, and as you can see, I can have multiple GPUs associated with a VM here, up to 4, and the GPU sends the data back that was requested back up to the guest OS and back to the application. That's the kind of full flow of a virtualized GPU here. And the virtual GPU, as I mentioned, might represent 1/4 or 1/8 or one portion of a physical GPU. That way we can have multiple VMs sharing the same GPU if we want to. And that's particularly applicable to the inference or deployment part of machine learning. At training time, at the early stages, at development time, you may say, let me give this particular data scientist a full GPU or 2 GPUs to work with. You can do that through vGPUs also. Next slide, please. So here's how I assign a particular portion of a GPU to a VM. On the right-hand side, you see the vSphere client user interface, and I'm deciding how many CPUs and how much memory at the top. But highlighted there in the middle is a choice of different mechanisms whereby a VM can use a GPU. Direct path IO is zero intervention on the part of the hypervisor. That's an option. Dynamic direct path IO allows you to use DRS placement. Even if you're in direct path access to your GPU, DRS will be allowed to place that VM onto the appropriate host that is capable of supporting that. And finally, NVIDIA Virtual GPU is what I've been talking about up to now, which is supported by those 2 drivers, a guest OS driver and a host driver. And this particular dialog is a result of me installing the host driver into the ESXi host. And what happens there is, now that I've chosen NVIDIA Virtual GPU as my mechanism for accessing a GPU, I'm given a set of profiles which determine, do I own this GPU completely, or am I really just sharing a part of it? And that's identified by the Virtual GPU profile there, which is for you as a system admin to choose. What this one is saying is this is an A100 GPU. It's the very latest. And this particular VM is getting 20 of the 40 gigabytes of frame buffer onboard memory. And this is a C or a compute intensive profile. This is particularly for machine learning. So DRS is helping you here in that it will now take this new VM and place it onto the right host with that profile. and say, I know there's that capacity available on machine number 10. I'm going to place you on machine number 10. And you can vMotion this VM from here onwards if you choose to. Next slide, please. So as mentioned, the NVIDIA Ampere A100 and the A30 actually is our sort of big brother and little brother in the machine learning world. The A100, the A30 are particularly designed for compute-intensive machine learning. And with all of the optimizations applied, these have shown 20x better performance than the previous generation. The A40 is more of a graphics-oriented GPU that's also supported on vSphere, but that's not applicable to our current subject here, which is compute-intensive and machine learning type applications. And at the really high end, we expect customers to distribute their machine learning application over more than one host server. That's called distributed training. And when you do that, there's actually quite a lot of communication going on between the pieces of your application on different nodes. And so you really want to accelerate that communication. And in the same way that Jason described, acceleration of communication to the storage, and storage is vitally important for these applications as well. What I'm talking about now is the use of GPU direct RDMA to accelerate the GPU to GPU communication that's essential in a distributed machine learning application. So you have a GPU on the left on server A talking to a GPU on the right on server B, and they're going via the network card, which is a Mellanox card, ConnectX-5 or ConnectX-6, which is RDMA capable. And the communication between those two is optimized in the way Jason described it. It's high speed, 100 gig, 400 gig communication over RoCE or over our InfiniBand. And the communication between the GPU and the NIC itself within the server is also optimized in vSphere 7 Update 2 by means of something that we call GPU Direct. And GPU Direct is optimized as a result of addressing mechanisms that we've improved on the PCIe bus called Address Translation Service. So that ATS or Address Translation Service is a new feature in vSphere 7 Update 2. And you'll be hearing more about that in subsequent releases of vSphere as well. Next slide. So just delving into the A100 here for a second. What you're seeing on the left-hand side is one or more physical GPUs on the PCIe bus. And on the right-hand side, you're seeing subsets of that physical hardware on one GPU that are separately allocatable to different VMs. Those separate subsets are called GPU instances. And they are in the past, we've had vGPUs around for machine learning for a long time, but in the past, we were really letting the cores be fully allocated by any one sharing VM. Here, with this new mechanism called Multiinstance GPU, what we're saying is that top box that I've surrounded with a dotted rectangle there, that is a piece of the hardware, both the streaming multiprocessors or the cores, the L2 RAM, the DRAM, and the system pipe, and the crossbar connections between all those. I'm isolating all of that now into one unit and allocating it to one VM. And I can collect two of these GPU instances together and allocate two slices of the physical hardware to one VM, or even all of the slices and allocate them to one VM. So as a provider of GPU power, I have much more control now over what subset of my GPUs any one consuming VM gets. And this is particularly for machine learning. It's not for graphics. It's really an enhancement to the GPU profiles that I showed you in the vSphere. There are newer profiles now for this type of MIG working or multi-instance GPU working. And it provides a strict isolation as opposed to a rather informal isolation in the past. This provides a hardware level isolation between one VM and another. And they're both consuming the same physical GPU, but different slices of it. So this means I can separate them out. There's no longer a noisy neighbor symptom in using this mechanism. And this is fully supported now in vSphere 7 Update 2 and later. So that's multi-instance GPU and how we support it through the virtual GPU mechanism. Okay. So now I'm going to pass back to Walt for more information on his work.
So really appreciate the insights, Jason and Justin. Clearly, there is a role for storage as part of this architecture and virtualized GPU world. Michael Kagan last year at Supercomputing 2020 made this quote that we think is spot on. High performance computing requires high performance IO. And it's not just about IOPS or throughput or latency. It's all about also storage density, the ability to scale as you grow in these environments, and having the flexibility to support multiple protocols, whether it's block, file, or object. So when Jason shared the performance data comparing RoCE and iSCSI, just straight up, that was work that was done by NVIDIA in their labs. And it wasn't about, hey, Pavilion's faster or better. We just wanted to get a fundamental benchmark. And I think you saw, 1.5 times the throughput, half the latency, really big differences. And that's enabled with RoCE. So we support RoCE, we support NVMe over TCP, and we were one of the very first to be part of vSphere 7 supported storage platforms. So kind of a nice fit here between the two or between the three organizations to deliver very high performance, very low latency. And how do we do it? Well, Pavilion's different. Pavilion is not a classic storage controller with 2 CPUs and some number of drives. We're built like a network switch. So 6.1 terabit backplane switching fabric, and 2 of those with many controllers, up to 20 separate independent storage controllers, each with their own CPU, memory, and network interfaces. Support for up to 72 NVMe SSDs. And these aren't, some special version of some special vendor's SSDs. These can be Western Digital, these can be Samsung, these can be Toshiba, Micron, depending upon capacity you're looking for, things like endurance that you may be looking for. We have the flexibility to offer multiple different drive types. And by the way, you can mix and match. So in our system, we have 4 separate zones of 18 drives where I could assign capacity drives to a zone, and I could assign very high performance drives to another zone. From a network perspective, 40 gigabit, 100 gigabit Ethernet connections, or 10 at 200. And again, those can be Ethernet or they can be InfiniBand to support this broader architecture that we've been discussing. And all of this in 4 rack units. So really nice, tight packaging to be able to do this scaling that we're describing. From a performance perspective and a flexibility perspective, what you end up with in 4 rack units is 2.2 terabytes of raw capacity, 20 million IOPS or 5 million IOPS per rack unit, 20 controllers, 40 network ports, support for block, file, object, and all the protocols that one would expect to see in today's modern data center, with incredible performance. And you can go to our website and look at some of the details around this. There's a solution brief entitled the Performance Solution Brief, which will give you more of a rundown on how we do file and object storage in addition to how we do block. But let's pick something that I think is meaningful and that Justin referenced earlier, which is this new GPU direct technology that NVIDIA is rolling out. Pavilion's been able to do benchmarking, and we're able to see extraordinary performance. And frankly, it's by getting out of the way, right? We need RDMA to communicate between storage server or storage and GPU and clear everything else out. and you can see really low latency numbers. And there's some good detail that's been featured on Blocks and Files, in particular by Chris Miller, about this CPU direct performance and comparing vendors. There's one more thing I'd like to do, which is, we speak about performance, density, scalability, flexibility, and so does the rest of the storage community. But what does it mean? And I think density might just be the thing that is the common denominator. And again, this is some work that Chris Miller did, and we have enhanced upon it, where if we could look at things like throughput or IOPS at a rack unit level, the common metric for data center measurements, you might come up with some really different perspectives on what a great storage platform needs to be. We've got competitors that do 350 gigabytes a second. Takes 2 full racks. So what we've done, and this is a blog on Pavilion website called Normalizing Data Storage Performance, Reporting Across Vendors. And there's a spreadsheet tool that you can download, plug in your own details, and compare that with other solutions on the market. You can look at it from the perspective of block or file or object, and get to some normalization state that might tell you what real performance looks like as normalized at the rack unit level. So highly encourage you to check this blog out, pavilion.io blogs, and normalizing data storage performance. So let's step back for a second. What have we learned today? vSphere 7 brings NVMe over fabrics to mainstream, support for fiber channels, support for RoCE. Update 2 enables this new NVIDIA Enterprise AI Suite with support for the Ampere family of GPUs, with near bare metal performance, with a variety of different functionality from VMware that's available or coming, and enhancements for GPU direct and address translation that Dustin described that I think is a real game changer for the industry. And for Pavilion, we're here to help enable this virtual world and virtual GPUs with universally unmatched storage, with performance, density, scale, and flexibility. And as Keith mentioned at the top, we are going to make this deck available. So there are a number of different blogs from VMware, website resources, and the same from Pavilion. So with that, I want to just kind of pause here, move to questions and answers, and let's go have a check and see if there are some Q&A things that have come across the wire. Keith, do you see any right now?
Thanks, Walt. Yes, we've actually had a couple of questions come in. And if anyone else does have any more questions, please feel free to go ahead and put them into the Q&A or the chat function, and we'll be sure to address them. In the meantime, a couple of the questions that have already come in says, my management wants us to move to containers along with VMs. They also want us to move to RoCE from Fiber Channel. Can I run both containers and VMs on vSphere 7?
Yes, this is Justin speaking. Absolutely. There is no problem with running containers within VMs, and you can think of VMs as a bit like the pod concept in Kubernetes, that they're a collection of containers that belong together. That's the kind of mechanism that's built into the core shipping Kubernetes that comes as embedded as the supervisor cluster in vSphere Tanzu. In your own cluster, if you're building sandbox clusters of containers and Kubernetes environments, a virtual machine can represent a host, and on it would run multiple pods, and within those pods would run containers. That's the kind of algorithm we use for the TKG clusters that Walter mentioned. So that's all there today. You can deploy it, and there's no problem at all with running containers within VMs. We're doing that extensively, and actually doing it for machine learning as well.
Great, thank you. All right, looks like the next question is, can I do MIG with GPU Direct under vSphere 7 Update 2?
The first part of that question again, Keith? Can I do?
Mig?
Oh, yes. Oh, okay. So MIG is an underlying technology that is represented to you as a user by those vGPU profiles. So provided you have an A100 in your hardware or an equivalent Ampere series, maybe an 830, provided you have that in your hardware, you turn on SRIOV at the BIOS level, and then you enable MIG at the ESX level on one or more of your GPUs, depending on how many. And at that point, then, if you've got the right vGPU VIB installed in your ESXi host, you can use the dialog that I showed in the slides to present that MIG virtual GPU to your VM. Yes. And that's been tested pretty heavily by NVIDIA and ourselves.
Great. Okay. And see, looks like the next question is, where can I download the storage vendor performance normalization tool?
Right. So that's what I referenced toward the end of the presentation. And if you go to pavilion.io and just go to blogs and look for the one that has the apples and apples, so red apple, yellow apple, green apple, click on that blog and that will give you a short story about what Chris Meller has written. And then there's a link to this spreadsheet at the bottom of that blog.
Okay, great. All right, and it looks like that would be all the questions that we have. So at this point, I'd like to thank everyone for attending this informative presentation. I'd like to thank our panelists for a great job. And we will, of course, make a recording of this presentation available to everyone who joined. In the meantime, if anybody would like some more information, please feel free to visit us at pavilion.io. Thank you.